Okay, in this part 3, we're going to talk about good conductors, which is a special case of radio waves propagating in lossy materials, in particular materials that have a lot of loss for the conductivity. So they are called good conductors, ironically, because they are very good at conducting current, which actually means that they are very bad at conducting radio waves or allowing radio waves through it. A good example of a good conductor is a metal, which of course is very bad at allowing radio waves through it. In fact, they almost perfectly reflect radio waves at most frequencies. So let's take a look at this. Remember, we had this notion that gamma equals j omega times the square root of mu times epsilon effective. And epsilon effective basically had 3 pieces to it. There's the real dielectric property, there is a lossy portion of the dielectric property, and there is J sigma over omega. There's a contribution of conductivity to this. Now, in the event that we have a very big sigma or very big epsilon double prime, epsilon effective will be very close to an imaginary number. If epsilon effective is nearly an imaginary number, then gamma will be very close to an imaginary number as well. And if you work through the math, what you'll find is that alpha equals beta for very large conductivity. So big sigma or big epsilon double prime, you'll basically get that gamma has the same value of alpha and beta. They work out to be the same. They both equal to the square root of pi times f times mu times sigma. All right, so let's take a look at this. What's the important part of this is actually the alpha, the attenuation rates. And what we're going to do is we're going to flip alpha and write 1 over alpha. And that's going to be 1 over the square root of pi times the frequency times mu times sigma. And this we're going to call something called the skin depth. Right? So let's think about what alpha is. Alpha is an attenuation rate in meters per meter. If we flip that over, it's what we might call meters per meter. That is basically the skin depth. So the skin depth is basically how far into the material can you go before you have a 1 over E reduction in your electric field. And so the skin depth is basically a measure of how deep you can penetrate a radio wave into a good conductor. And so let's take the example of a perfect conductor, and you've got a radio wave that is reaching that boundary. We're going to talk about what happens in the next lecture, but I'll give you the spoiler. There's going to be a reflection that's going the other way, much like a transmission line hitting a short circuit. Now, if this were an absolute perfect conductor, sigma would be infinite and the skin depth would be 0, which means that the radio wave basically induces current right along the surface, and there's no electric field inside the material. But for any realistic material, sigma is not going to be infinite. It could be a big number, but it's not going to be infinite. And the skin depth is basically going to tell us you get a little bit of the radio wave propagating. It's going to weaken as you go deeper into the material, but there's basically going to be a slow exponential drop off, and you get a little bit of penetration. This is basically called an evanescent wave because it's not really propagating, but the material does not have enough conductivity to completely block it. And so you get a little bit of electric and magnetic field within this region. It's dropping off fast, but it's still there, right? And the skin depth tells you about how far it goes. If you go 1 skin depth into the material, again, you get a 1 over E reduction in your electric field. Now, what's neat about the skin depth is you can see that it is inversely proportional to the square root of the frequency. And that seems a little bit unusual because what that tells us is as we go down in frequency, we're getting actually deeper penetration into seawater, or sorry, forget seawater, into a good conductor. And this may seem strange because if we go back to the formula for epsilon effective, and let's examine this for a second. If omega gets smaller, then this third term right here gets bigger. And so you would think that the complex term is dominating even more as you reduce your frequency. But what's actually happening is sort of two factors that only partially cancel each other out. As you decrease the frequency, the attenuation per wavelength is going up, but the wavelength itself is also increasing. And the attenuation per unit wavelength basically goes as the square root of lambda, right? So as the wavelength gets longer, the attenuation rate only goes up as the square root of it getting longer. Whereas as we drop the frequency, it scales inversely with the wavelength. So that's a lambda. So in net, as you shrink the frequency, you get actually deeper penetration in terms of real number of meters. And so that's why in the skin depth formula, there's a square root of f in the denominator. And this is called the skin effect. And this is, by the way, important for why, when we talked about a coaxial cable, for example, and we talked about the idea that the current does not penetrate through the entire inner conductor, but is actually confined along the surface. And the lower we go in frequency, the more it can fill that entire conductor. But if you go up in frequency, then you're stuck to only have your current in a narrow shell on the outside of your conductor. And that actually gives you a little bit of resistance. And that was called the skin effect. Now that we are here, we can sort of explain that with real physics, given this notion of how the skin depth changes with frequency. Now let's take a look at some examples for real materials. So for a metal, we've got a frequency of 1 gigahertz, and I'm going to assume a conductivity of about 10 to the 7th, which is kind of realistic for aluminum, for example. At a frequency of 1 gigahertz, the skin depth is about 5 micrometers, right? If you go down all the way to 1 kilohertz, however, it's higher. It's more like 5 millimeters instead of micrometers. So you start to get a little bit of noticeable penetration into a metal if you are at especially low frequencies of 1 gigahertz. All right. Let me kind of show you what this looks like pictorially with a little video here. All right. And this is basically a good conductor compared to a conductor that's not a very good conductor. And so these are 3 different plots. I'm going to play all 3 of these. The left plot is a material that has no loss at all. The middle plot is a material that has a little bit of loss, but not very much. And the right is a good conductor where you're dominated by losses and have little to no penetration. And the red line is the exponential attenuation, that's alpha, and blue reflects the phase evolution of the wave as it attempts to penetrate inside the material. So this is basically how a good conductor case compares to a low loss conductor, or really is a good propagator of radio waves. But one thing that we can learn from this, and it's very applicable to the idea of GPS, is that GPS, as you may know, it does not really work underwater or in, let's say, the basement of a building, because seawater is actually a pretty good conductor. In particular, it's a salt that's in seawater that makes it a good conductor. It's got a conductivity of about 4 for seawater. So here's your little GPS satellite, and it's broadcasting signals. And as soon as that signal reaches the seawater floor, it encounters what ends up being a very good conductor, and it very rapidly attenuates and disappears. So if you go underneath the seawater, you basically cannot detect any GPS, and you really can't communicate with anything above the surface because of this fact that, again, seawater is a good conductor, and you got to go really high in frequency before it stops being a good conductor. However, there is an application for which you can penetrate something underwater, and that is if you reduce the frequency. So if we come back over here, and come back to this formula, if you plug in a value of sigma that's equal to 4, and you reduce your frequency far enough, once you get into the kilohertz range, now you've reached a point where you can actually get some reasonable penetration of many meters, tens of meters underneath the seawater. And that can be very useful for certain applications, in particular submarine communications, which is primarily done with very low frequency waves down in the tens of kilohertz range. And the idea is you've got seawater, and you've got a radio wave here at, let's say, 30 kilohertz. Seawater is still a good conductor, but you have a big enough skin depth that it's going to penetrate far enough down beneath the surface that your little submarine down here, tens of meters, can now listen into those signals without having to surface. And this is actually the state of the art for how submarine communications is done, and it's been this way for many decades now. This is actually a picture of one of these radio stations in the low frequency band of a few tens of kilohertz. And the problem with low frequency waves is the wavelengths are enormous. They are many tens of kilometers long. And typically that means you need to have an antenna that's as big as you can possibly make it in order to broadcast. So this is actually a diagram of an antenna that's in Washington State. It operates at 24.8 kilohertz. And the actual antenna is actually the center structure, but all of these wires over here is basically required to get a reasonably efficient antenna. Take ECE 4370 and you'll see a lot more about that. But this enormous antenna right here is basically thousands of acres long in order to be able to produce this signal. But while this facility costs many millions of dollars to operate every year, it is worthwhile because it's pretty much the only way to get a radio wave under the sea surface, where you have kind of a reasonable enough connectivity. So just an application of where good conductors and skin effect can kind of come into play. So that's it. I'll conclude this lecture here on good conductors. We've left something on the table, which is describing the way in which radio waves can be oriented and also the way in which they can reflect off of materials. And we're going to be covering those in the upcoming lectures.